So we have pressure equals to force over area. And the force here, we're only talking about gravitational force. So that's mg. So mass times acceleration divided by area. And mass equals to density times volume times the gravitational acceleration g over a. And volume equals to a times h. So rho a hg over a. And obviously this area can cancel out. And we end up equals to P equals to rho GH. Quick refreshment on your physics. So if we do all the calculation, you can get 1 torr equals to 133.322 Pascal. And you can check this number by doing all these calculations. If we know, like, say, the mercury density is 13.5951 gram per centimeter. So torr is one of the units we will be using. And you should expect to know, like, how to convert between different units of pressure and volume later on in this course. Other common unit we use for pressure includes atmosphere, or ATM. So 1 ATM is about 750 torr, or 1 bar. Bar is just the approximation version of the atmosphere. They're really close to each other, but they're just a little bit different. And for the volume, we have 1 liter equals to 1 dm squared, or like 10 to the minus 3 meters squared. cube, sorry. So again, this is a quick review for your physics. Again, you should expect to know how to interconvert between different units of your pressure and volume. Okay, and now we're ready to actually talking about the ideal gas law. I know we spent so much time reviewing of all the concepts and so on. So for the ideal gas law, we will start by looking at 2 fundamental experimental results. So as scientists, you're always looking at some kind of experimental observation. And what we're trying to do is get a general understanding or generally applicable theory from these experimental observations. So the 2 experiments we are looking at, one is called the Boyle's law. So it's an experimental law originally done in 1662. So it's a long time ago. What the Boyle's law is actually looking at is a relationship between pressure and volume of some kind of a gas. The gas they choose to use is nitrogen, but effectively any gas can suit for this property at constant pressure. So for looking at the scientific figure, we'll be looking at these figures a lot. So here's the general way I hope you can get in how to read a figure you never saw before. So we always start by looking at the y-axis. So that is pressure. And ATM tells you the unit of pressure is in atmosphere. On the x-axis, we have volume. And the unit of volume we use is in liter. All right, so the first thing first is we always look at the coordinates and get an idea. Okay, so we're looking at a relationship between pressure and volume of a gas at some temperature. Now we have 2 different curves here. Every curve represents a measurement taken at a different temperature. So this curve here on the bottom is taking at negative 75 degrees Celsius, and this curve here is taking at 100 degrees Celsius. So both curves are taken at constant temperature. But what exactly that temperature is, well, you can do multiple measurements. So with the help of math, we have an idea about what this type of figure tells you, right? So the shape of this line tells you this is likely to be a equation like y equals to some constant over x. Now y here is our pressure, and x here is our volume. Or taking together, the relationship we're getting using the boiler's experiment is that the pressure equals to some kind of constant divided by volume at constant temperature and constant mass of that gas. So typically we use the small letter k stands for some constant. All right. So just a quick refreshment. So in this experiment, remember we have the experiment taking at constant temperature and constant mass. Now, is our system an open system, closed system, or an isolated system? Well, that's different. So is our system an open system or a closed system? Well, we have like material exchange between and inside and outside of the system we're measuring. It is constant mass, right? So the mass of the gas molecule we're interested in is not changing. So my system is likely to be a closed system, just to make a connection there. All right, so that's the Boiler's law. The relationship we're trying to make here is the pressure times volume of some kind of gas at constant temperature and constant mass gives you a constant. So that's part one. Part two is the Charles law. It's developed in 17th, 18th century. So the idea here is to look at the thermal expansion of gases. So again, we always look at our coordinate first. So on the y-axis, we have our volume. In liters. And on the x-axis, this is theta, so that's what we call the thermometer temperature because we haven't defined the thermodynamic temperature, but you can treat it as a form of temperature. In degrees Celsius. And you have multiple lines, and each line is measured at constant pressure. You can have different pressure there, but they're all measured at constant pressure. It's a linear relationship, right? So for any linear relationship, we have y equals to kx plus b, where k is your slope, b is your intercept. So in here, what we have is volume of a gas equals to some constant A1 plus some constant A2 times the thermometer temperature theta. And this is true at constant pressure and mass. All right. And then using the Charles law observation, we can then define a new temperature scale that's more generally applicable. Like it's not rely on some kind of thermometer to define that temperature, right? We want something that you can just grab and use. You don't have to say, oh, it's just a temperature coming from a mercury thermometer. So from the Charles law, we end up being able to define the ideal gas absolute temperature scale. So what exactly that means is if we take the extrapolation, so the actual measurement cannot go all the way to absolute zero where the volume of that gas becomes zero, right? So, but we can extend our linear relationship by measuring that curve at different pressure. And by doing so, we find out these lines will eventually intersect our x-axis to our x-axis at about negative 273 degrees Celsius. At that point, we use to define our absolute 0 degree for our thermodynamic temperature scale. All right, so what we're saying is that Charles' law holds exactly when our pressure goes to about 0. And when our pressure is approaching 0, the temperature just equals to some kind of constant B times the volume. And yeah, so this is the full text we just talked about. It's actually talking about any gas. Again, in the original Charles law, we use nitrogen gas, but effectively you get the same measurements, whichever gas you like. And our absolute 0 for our ideal gas temperature scale is defined to be about negative 273.16 degrees Celsius. Or the other way to put it is the triple point of water is exactly 273.16 Kelvin. All right. So one of the things you might think about is, well, if you went back in time, back to the 1600, and nobody knows about the absolute 0, how do you design an experiment so you can measure the absolute 0 temperature? Or in some random universe, right? You're trying to measure the absolute 0 for that universe. How do you set up your experiment? Okay. And before we move on, let's just do some quick example questions together, because we will be using these techniques by moving terms around and get an idea about what temperature is, what pressure is, using different kind of information. So if we just look at it together, in our problem 1, we have 10 to the 5th Pascal, P over bar equals to 9.4. And the question asks about what is P. So what we're doing is just moving things around. So P equals to, on the top we have 9.4 bar over 10 to the 5th, or 9.4 times 10 to the negative 5 bar. Right, so if we look at number 2, that's the same idea. We have the 10 to the negative 2t over k equals to 4.6. And asks for what is t. So we can move terms around to get 4.6 times 10 to the 2. Okay. You can try it yourself. I mean, it's not hard, just get familiar moving things around. All right. Do we have any questions before we move on to talk about the actual ideal gas law from Boyle's law and Charles' law? Yes.
Sorry, from the previous slide, what is A? You said A was a constant?
Yeah, A1 and A2 are just random constants.
Okay.
You can get a different A1 and A2 from different slope.
Okay.
So we can't specify it. Right. All right, so now let's look at the more generalized version of the ideal gas law. So here we have two relationships, or basically what we want to do is derivation of our ideal gas law. I can't hold a secret because everyone knows what ideal gas law looks like in this classroom. But let's see how we can actually derive the ideal gas law from the two experimental observations we just made, which is Charles' law and Boyle's law. From Boyle's law, we have PV equals to K. So pressure times volume of some ideal gas, it gives you a constant K at constant temperature and constant mass. And then we have Charles' law, where volume equals to A1 plus A2 times T at some constant pressure and constant mass. But how about my pressure, temperature, and volume are all changing along the way? What is the relationship between pressure, volume, and temperature? So the way to think about it in thermodynamics, we always try to imagine a path that these transformations can take place. So we're gonna work on it together here. Now let's imagine an initial state where you have P1, V1, T1, and some kind of mass. Because mass is always held constant, I'm just gonna not mention it. And effectively, what we want at the final state is we have our P2, V2, and T2. So everything changed. My temperature, pressure, and volume all changed from initial to final state. So none of the two relationships we can use directly to predict things when pressure, temperature, and volumes are all changing. But what we can do is maybe we can do it in two steps. The first step is we keep temperature constant. So with our temperature held constant, we can use our Boyle's law. Right, so what we have is P1 V1 equals to P2, some kind of volume A, equals to K. Right, so after our initial state to our intermediate state, we're changing from P1 to P2, and we're changing from V1 to some VA, and the temperature is held constant at T1. And that's the relationship we get, is P1 V1 equals to P2 VA. And then the second step here, now we have P2 already the same, so we can keep the pressure at constant, and we can use Charles' law. So in this process, we have pressure constant, so if we're talking about the Charles' law, where we have V equals to A1 plus A2 times some kind of T, or if you move the terms around, what we have is V divided by T, well, equals to some constant, right? So at constant pressure, your V over T always gives you the same constant A2. Or in here, what we have is V2 over T2, that's your final state, equals to VA over T1, that's your intermediate state. And that gives you some constant A2. All right? Or taking together the two relationships we have is P1 V1 equals to P2 VA, gives you constant K. And here we have V2 T2 over T2 equals to VA over T1 equals to some constant A2. And moving the terms around, what we end up having is VA equals to P1 V1 divided by P2. And then on the bottom, now we can substitute this VA into here, and we end up having V2 over T2 equals to P1 V1 T1 P2. And then let's move the things around. So your 2 stays with 2 and 1 stays with 1. You end up having V2, P2 divided by T2 equals to P1, V1 divided by T1. I'm just moving this P term here. And this equals to some constant. Right, so that's how we get our generalized ideal gas formula, PV equals to nRT. Where nR are the two things. Well, n is the number of moles, and R, that's the constant we actually used. All right, so far what we did is for ideal gases, what exactly chemists are doing is we have a simple observation that the equal volume of different gases at same temperature, T, and pressure contains the same number of molecules. We always have PV equals to NT, PV over NT equals to R, where R is our ideal gas constant. All right. And there are several different variations of the ideal gas law. You can imagine the same idea here if you replace the number of mole with mass and then the relative mass. You get PV equals to the actual mass divided by the relative mass times RT. Or you can introduce the idea of density when using the ideal gas law. So your density equals to mass over volume. So you can introduce density there and write the variation of the ideal gas law with density of the gas. So these are examples of equations you don't have to remember. But for example, if you encounter a problem that only gives you density but no information about volume, well, you might be able to transfer and use a different equation. And here's, I just want to emphasize again, like, don't just go jumping and find an equation to use. Like, really think about it. Like, what equation is more relevant to the problem of interest? And for ideal gases, because my gas molecules, they don't really interact with each other, so the total number of moles will give you by N1, N2, N1 plus N2 plus N3, and we should have no problem with it. And you can use our partial, well, you can use our mole fraction to have the a different version of the ideal gas law. Right, so you can imagine here the partial pressure equals to the mole fraction times the total pressure. And your mole fraction is defined by the number of moles divided by total number of moles. So your partial pressure, PI, is defined as NI RT over V. Okay, we have about 15 minutes, so I'm gonna skip this practice problem here. You can try it yourself. Just plug in numbers and get familiar moving things around to find the information you need. So in short, so this one you want to use the equation P equals to rho RT over mass, right? Because we know the density, but we don't know too much about its actual volume. So that's why we're using the density version of the ideal gas law. All right. Our last topic of today are equations of state. So here we're jumping in to even more generalize what we learned about the ideal gases and what exactly does ideal gas law mean. So here, the general idea of equations of state means that for every specific system, there exists an equation state. So that equation state tells you the relationship between pressure, volume, and temperature and amount of substance of that system of interest. right? So for any system of interest, you can imagine this bottle of hand sanitizer, you have a relationship that's linking these macroscopic properties, pressure, volume, temperature, amount of substance, together with each other. So if we're looking at the volumetric version of equations of state, means we're representing volume of that system with a function of pressure, temperature, number of moles, and etc. So that's called the volumetric equation of state. You have different versions, of course. You can have the pressure version, right? So pressure is a function of volume, temperature, and number of moles, but they're effectively related to each other. Now, unfortunately, we don't have something that's generally applicable. So equations of state are need to be determined experimentally, like the ideal gas law, right? We did our Charles law experiment and then the Boyle's law experiment. We use these two experimental observations together to derive the ideal gas law. And that is the equation of state for ideal gases. But for some other system, like our bottle of hand sanitizer, you need a different set of equation of state. You can't use the ideal gas law for the liquid in there, right? So those are only determined experimentally. Now this one is just what we just said, equation of state of any, equation of state of any pure one-phase system has a relationship, so you can take that number of mole out from that system because your volume is an extensive property. So for anything that's pure one system, your number of moles, you can just take it out and know it's just a proportional to your volume. Or sometimes we also use the notation of molar volume. So that's V, capital V, with a subscription of small m. So that's the volume divided by the number of moles. So for example, for an ideal gas law, we have PV equals to nRT. So you can write the volumetric equation of state, V equals to nRT over P, or your molar volume equals to RT over P. And just as I said, for a different kind of system, you can have different state equations of state. So if we expand ourselves a little bit beyond the ideal gas law, now imagine you have Van der Waals equation of state. So now instead of assuming gas molecules don't interact with each other, the gas molecules now will interact with each other via two different ways. The first way is, say, gas molecule attracts each other at certain distances. And then if you treat our gas molecule as little like solid balls, they will also repel each other. Right, so taken together, you have a different set of equation of state describing the Van der Waals gas, which more closely related to what experimentally observed. So some of the things we will do pretty extensively is know how to play with these equations. It doesn't necessarily produce a numeric number, but know how to move things around to get the expression we want. So if we use our Van der Waals equation here, ooh, weird. So if we use this Van der Waals equation here, you could be asked to write out what are the units for these constant A and B in your Van der Waals equation. Right, so for example, if we're looking at this V minus MB. So because you can do plus and minus between volume and MB, so these two will have the same unit. Or the other way to put it is your B has the same unit as your molar volume, Vm. Or some typical unit you can put is like cm cube over mole. The same idea for your constant A, right? You can write it out. What's the unit for that constant in this relationship? All right. And at the very end, now come to the question is, why do we care about all these equations? And the answer here is that thermodynamic, or these states of equations, gives you a way to measure this intrinsic relationship between pressure, temperature, and volume, and effectively we will have new state functions like entropy, enthalpy, internal energy. So the idea here is thermodynamics gives us a way so that we can measure these properties, right? So it's easy for you to say like, hey, can you measure the volume of a cup of water? It's hard, but it's something you can measure, or the mass of a cup of water, or the pressure of that system. But what if I ask you to measure how does your entropy change with temperature change? So that's something, we don't have something called an entropy thermometer, and that we use our thermodynamic relationships to do it. The straightforward application here, I just want to quickly introduce the relationship between these macroscopic properties, volume, pressure, and temperature, using partial derivatives. So some of the terms we will be using are called isothermal, isobar, or isochoric processes. So what these terms mean? Isothermal is, judging by its name, just saying this process will consider it taking place at constant temperature. Or if you go back to our partial derivative, right, Vm is a function of pressure, temperature, then at constant temperature, you can write out the partial derivative of your molar volume over pressure at constant temperature. And using the relationship here, remember in calculus, we have the partial derivative of z over x at constant y, well, equals to 1 over partial derivative of x over z at constant y. So that's in calculus. So what that tells me is we can write this relationship here as a pairwise. So your partial derivative of pressure over the molar mass at constant T, well, equals to 1 over partial derivative of Vm divided by partial derivative of T, P at constant T. Right, so just moving terms around using basic calculus. Using that same logic, you can build the relationship for isobaric process, means constant pressure. T over Vm at constant P equals to 1 over Vm dt over P. And likewise, for isochoric, we have the constant molar volume. So Vm is held constant. And we have partial derivative of T over P at Vm equals to 1 over partial derivative of P over T at constant Vm. Right, so now we have 3 pairs of partial derivatives that are connected to each other. The next thing we want to use is the chain rule. So if you remember the chain rule, if you take the partial derivative like 1 by 1 at constant z, x, and y, you end up having -1. So if we go back and write our relationship, what we have is your partial derivative of P over Vm at constant t, partial derivative of Vm of constant t over t at constant p, and partial derivative of t over p at constant Vm gives you negative 1. All right. And then moving things around using our relationship again, which is here, using our calculus again, you will end up having the relationship of partial derivative of P over T at constant Vm, so that's this term here, equals to negative P over Vm at constant T at constant P. Or, in order to better measure these properties, it's easier for us chemists to model the change of volume at certain condition, right? Whether it's isothermal or it's a isobar process. So the two easy to measure relationship, you can think about measuring the partial derivative of your molar volume over either pressure or temperature. So we can further rewrite this term. We can make a little bit space. That gives you the negative on the top, partial derivative of Vm divided by partial derivative T at constant P, and on the bottom we have partial derivative of Vm over P at constant temperature. So effectively, what we chemists are measuring are just these two partial derivatives that gives you the relationship of temperature, pressure, and volume. So that's just generally true. That's how experimentally, what kind of experiment you should be designing if you want to find the actual relationship between P, T, and V. We will go back to this coefficient, but let's just give them a name because we will be using it. So the first one here will be called alpha, which is a function of temperature and pressure. So that is called our thermal expansivity or cubic expansion coefficient. So what this alpha is measuring is how much your substance expands with respect to temperature at constant pressure. Alternatively, you have the isothermal compressibility. So now the isothermal compressibility chi, it looks like a small k, but it's effectively the Greek letter chi, which is a function of temperature and pressure. So that's something you can measure. It's called the isothermal compressibility. Okay, so tomorrow you'll be working with your TA on discussion worksheets. I'm not sure if you're gonna have a discussion worksheet due this week. Check with your TA because we only get started with our lecture. But chances are he will tell you more information tomorrow. So tomorrow, same place, your TA will be here with you. I'll see you on Wednesday.